Hi everyone. Today my colleague Derbanosov and me, Bakhanova Maria, are going to present you our research about stability of topic modeling via modality regularization. Here is a short outline of our talk. And let's start with an overview of topic modeling. What is topic modeling? This is a statistical method for analyzing the corpus of documents. We want to highlight two main goals of topic modeling. The first one is to find topics that can give us information about the inner structure of large corpus of documents. And the second one is to find hidden representation of documents and terms and use them for different machine learning tasks such as text classification, recommender systems, chatbots, and sentiment analysis, and many other tasks. The result of topic modeling is a set of topics. But what do we mean by topics? In this study, we want to define topic as a discrete probability distribution over a set of terms. You may see some examples on the slide. So for each term in the topic, we have some corresponding probability, which is a number between 0 and 1, as usual. The most popular algorithms for topic modeling solve the task of stochastic matrix factorization. Let's denote that D is a collection of documents, W is vocabulary, so set of all words in documents, T is a finite set of topics, and usually the number of topics is fixed before running the model. So the idea of stochastic matrix factorization is to find an approximate representation of a stochastic matrix F as a product of two stochastic matrices phi and theta. Matrix F is usually called word document matrix. Each element of this matrix is the number of occurrences of a particular word in a particular document. So rows in this matrix stand for word indices, and columns stand for document indices. Columns of a matrix F are normalized. Matrices phi and theta are called word topic matrix and the topic document matrix. You may note that if we fix some stochastic representation, so if we fix phi and theta, we may consider distributions in columns of the matrix phi as topics. Yeah, and this factorization is called stochastic because all three matrices, F, phi, and theta, are stochastic. The most popular approaches to the topic modeling are probabilistic latent semantic analysis, PLSA shortly, and latent Dirichlet allocation, LDA. The basic hypothesis of PLSA model is the conditional independence hypothesis. So the probability of a word occurrence in a document is conditionally independent of the document given topic. We may think that LDA is like a Bayesian version of PLSA, and the main assumption of LDA model is that elements of matrices phi and theta are generated from the Dirichlet distribution. In this study, we focus on PLSA algorithms and its modification. Therefore, let's discuss PLSA in more detail. According to PLSA, the term distribution in each document D can be decomposed as the sum over all topics of a product of elements of matrices phi and theta. So you may see the formula on the slide. Parameters of matrices phi and theta are estimated via maximizing log likelihood function with linear constraints. You can see the loss function. It is described on the slide. We use expectation maximization algorithms to find those matrices. Additive regularization of topic models, shortly we call it ARTM, is a modern extension of PLSA. The idea of ARTM is to add different regularizers to the loss function. So suppose we have an regularizer that we want to maximize along with the likelihood L that we have described before, and in ARTM we solve like a multi-criteria problem via maximization of the linear combination of our previous laws L and regularizers with some non-negative coefficients tau. Here we present some examples of regularizers. So the first one is smoothing regularizer. The idea of this regularizer is the following. If we want elements of matrices phi and theta to be close to some discrete distributions, beta and alpha, in terms of Kullback-Leibler divergence, so we can use this regularizer. The effect of this regularizer is an increase in small values of phi wt and theta td due to a slight decrease in their large values. As a result, generated topics may include general vocabulary words, stop words, and rare words that are usually excluded from topics. The second one is sparsing regularizer, and usually we assume that each word in each document relate to a small number of topics, and it means that matrices phi and theta should be sparse. And we may achieve this using sparsing regularizer. One may notice that the sparsing regularizer is just an inverse procedure to smoothing. Therefore, sparsing regularizer differs only in sign. There is minus here. Yeah, and the last one is decorrelation regularizer. It formalizes the requirement that topics have to differ from each other, and it can be satisfied via minimizing the sum of covariances between distributions phi with WT and phi WS for all pairs of topics T and S. Let's talk about multimodal topic modeling. Usually documents can be described not only by natural language words, but also by terms of other modalities, such as tags, engrams, named entities. Even pictures and website can be additional modalities, so they can be additional metadata that we can use for determining topics. Let's discuss how do we work with modalities in terms of matrix factorization. Let M be a set of modalities, WM be vocabulary for modality M, and as you may see on the picture, we introduce the same as previously, the same matrix factorization task. So we have a matrix F, M, and we want to represent it as a product of two matrices, phi M and theta. Once we define the matrix factorization task for one modality, and we can extend this problem to the problem with a set of modalities. As for distribution of words in topics, the matrices phi M are normalized separately and stacked vertically into the matrix phi. You may see the picture on the slide. Note that the matrix theta is the same for all modalities. Let's go to modality regularization. And here the idea is the following. If we consider the log likelihood of each modality as a regularizer with some coefficient tau, then the optimization problem has the following form. You may see the formula, and you may notice that the only one thing that is different from a standard PLSA optimization problem is that we sum the log likelihood over all modalities. And also we have the same linear constraints here.
Most topic modeling algorithms use random initializations and then they converge to some local optimum. Here we meet one of the main problems of topic modeling, instability. That means that if we run our model from different initializations, then we will converge to different topic models. There are two main approaches to this problem. One of them is mathematical study of underlying problems, and the other one is replacement or modification of topic modeling algorithms. In our work, we propose a method of increasing stability with the help of multimodal topic modeling. Okay, how do we measure our quality? First of all, we have to measure the quality of our topic model. Usually, if we have already built topic model, we may see on its topics, on its top words, or some other kind of description of our topics. And then we may ask people to measure some scores. One of the most popular is interpretability of topics. But if we want somehow to measure the quality with some automatized score, we want to use some approximation of such scores. One of them is coherence. The main feature of coherence is that it reflects the interpretability of topics better than any other known metrics. It has a parameter k that is a number of top words that we use, and let we have some set of top words for each topic. Here on the slide, you can see a formula for coherence. Okay, what does it mean? Actually, you can see that it's some normalized expression, and near logarithm we have p of u and v. You may think roughly about it as a probability to meet two tokens u and v in some document of our collection. And also it's normalized on the probability to meet each token in our collection. Okay. To measure stability of our topic model, we use slightly modified metrics that other authors mention in other papers. It's actually you can see that it's first of all, if we want to measure stability, we should have several runs of our model. So first of all, we have normalization coefficient for our runs. We assume that we have R runs of our models, and we have T big models. So we have two normalization coefficients, and then we have sum of the expression named stable words. Okay, how do we compute it? Actually, we have two different models. We can make a matching between these two models So actually model as a set of topics. Then we can take a look of on topics of two different models and make a matching, for example, using Moncrief's algorithm between these two sets of topics. So if we have some topic S from the first model, it has a matched topic P of S from the second model. And then if we have two roughly similar topics, we can measure stable words in these between these two topics. We just take some top words and then we compute the size of intersection of these two sets of top words. Okay, in order to make our experiments, we used several data sets. I can divide them into groups. One of them is 20 NUBS groups, Realtor-Skate, and WebKB. These data sets are actually for text classification tasks. So they have tags and labels of these tags. And we use both tokens as modalities. And we also used Haber dataset. It doesn't have any kind of labels, but it have tags, hops, users, and authors modalities, and of course, words. In the next slides, I will give you an overview of results on 20 news groups and Haber. Okay, now about the pipeline of our experiments. So if we have some data set, first we do some preprocessing. That means that we delete some words and use stemming. Then we divide the data set into parts, train and test. After that, we train big RTM model and push this model to the test pipeline that measures our coherence and average stable words metrics. And we do a lot of runs, for example, 100. So after that, we just average these two metrics or all runs. Okay, here are results for 20 news groups with number of topics equals 10. So in the first column, there's description of the model and modalities that we use. So of course, first of all, we use modality named words, and we use some percentage of labels. It means that if we have in the data set all texts are labeled, but for our experiments, we delete some part of labels. 5%, for example, we leave only 5 or 20, 50 or all labels. And we did it to simulate the case that you have huge data sets and you have opportunity to label only some small part of this data set. Also, we used usual regularization techniques like decorrelation, parsing, smoothing. So here are results, and the main thing I have to mention is that the big amount of labels you use, the more stable results you have. But there's a drawback that's in the same time then the average stable words metric increase, the coherence decreases. And here we can see about the same results. So the we didn't use some percentage of these modalities, but we tried different combinations, and the most stable results we have if we use all these modalities. Okay. As I mentioned before, modern topic modeling approaches with random initialization suffer from instability of their results. If we use some kind of additional information, for example, labels or text, we can use it in order to increase the stability of our topic model. Even if we have a small amount of labeled data, in this case, you also can increase the stability of the model. The drawback of this method is if you use a lot of labels and a lot of additional information, your model may yield low coherence score. But also we have to mention here that even if the coherence score is low, in our experience, we saw that interpretability of top words of topics is still high. Thank you for your attention.